In the previous lesson, we defined how to express the uncertainty in a measurement. Today we're going to look at the actual act of taking readings when you're doing an experiment, and we're going to define accuracy and precision. We're also going to start to differentiate and give examples of systematic errors and random errors. By the end of today's lesson, you should be able to define all of these four things, and give examples. Precision. A result is precise when similar measurements are obtained using the same method. The results may not be true or accurate, but they are repeatable. Let's say, for example, that you are measuring the time for the complete swing of a pendulum. It might be that you are using a stopwatch, which is just not very good, or that you're not being very attentive. All of these factors might have an influence on your results. But we would say that your results are precise if you measure how long it takes for one swing. That means from here to here again. And your results always come out to look the same. So if you get 4.1 times 10 to the minus 2 seconds, you always get that answer. We express that here in our dartboard as a metaphor. Basically, it doesn't really matter if you're getting the right answer. What's important, if you have precise information, is that whenever you take your stopwatch to measure this pendulum, you're always getting the same answer. So that's precise. Accuracy is very different. Accuracy actually relates to the quality of the result. How close are you to the actual true value? And we show that here on our bullseye, or whatever you want to call this. We show it as close to the bullseye, right? That's the actual result, and your readings are pretty much spot on. Here you can see that they're not precise. You're not getting the same point, but at least your points are around the actual bullseye. So let's say, for example, the pendulum swing here is 4 times 10 to the minus 2 seconds. Then if your readings are giving you 3, 3, 3, 3, they're precise, but they're wrong, right? So they're not accurate. If you take these readings and you're getting 4.3, 4.2, 4.1, 3.8, then they're close to the true value, but they're not precise. Okay, this is another quick example. If you have 100-gram mass, you put it on the mass balance, there it is, spot on. You try it again, and this time you get 98.89. It's close, but it's not the right value. You keep repeating it, you still get the same 98.89. So it's precise, but it's not accurate. Throughout all the experiments that you're going to be doing, including your IA and possibly even extended essays, you'll be faced with the following 4 scenarios. You might have data which is not precise and not accurate. That's the worst case scenario. That means that you are repeating your experiment over and over. It's giving you completely different answers, and you are miles away from your predicted. You might get data which is precise but not accurate. Now, that's actually a really interesting situation, and it's to do with your instrument and the way you're doing the experiment. If you get this and you figure out what exactly is causing that problem, that gives you a stellar evaluation. Here we have a situation where you're close, but you're not precise. Now, basically, that could be because you're not using an instrument which is appropriate to the experiment you're doing. You might need to use an instrument that's going to give you much closer results. You'll need an instrument which measures to the next 10th of a measurement or 100th, a much more delicate and precise instrument. And there we have the ideal situation, which you will all have eventually, I hope, a situation where your data is precise and accurate. Now, a note on accuracy. How do we know if something's accurate? You're only going to know if you have a prediction. So the first one would be if you're finding acceleration due to gravity. That will be the first experiment we do. You're going to prove that G equals 9.81. And that is your starting point. If you're doing an investigation where you don't actually know what your predicted value is, then it's going to be very, very difficult to judge if something is accurate or not. However, we'll talk more on this as we start doing investigations. Now let's start talking about errors. Random errors arise from random fluctuations in measurements. Arbitrary is another way of expressing this. It's an error which will happen once, and it's very difficult to get that error happening again. You may encounter random errors in this experiment where you're measuring the temperature of melting ice, because where you put the thermometer will very much control the temperature that you get. So if you put your thermometer here, you're going to get a completely different reading to where if you put it here or if you put it here. And that effect is random. Now, you can do things to your experiment to avoid random errors. Like in this one, you'd have to think and try and plan ahead, and stirring would reduce it. Or if you were doing an investigation, you would ensure that you always put the thermometer in the same place, for example. Random errors occur randomly around your value. If we have a look at this, this is showing you what random errors look like. They're not all on one side, they're not predictable. So it's quite easy to spot eventually when you plot your graph which ones are random errors, because they literally scatter in unpredictable ways. There are many reasons for random errors. It could be the limitations of the instrument or display you're using. It could be that your method isn't careful enough. It could be that you are reading scales from wrong positions. I'll talk about this in a minute. This is called a parallax error. It could be irregular human reaction times when using a stopwatch. Sometimes we consider this to be a different kind of error, systematic, but it can also be random. And if you're making observations that change quickly over time. In general, random errors happen because you're not being careful enough, you haven't planned your experiment carefully, or because of something completely unpredictable. Parallax errors are to do with the way that you read a scale. You must always read scales, whether it's volume using a measuring cylinder or if you're using a ruler, but you must always measure them at eye level. If your eye is either too high or too low, you will end up having a reading which is dependent on your original position. Now, if you are constantly changing that position, like say you're measuring the extension of a spring on a ruler and you're having a chat with your friend, and then you look from here the first time, here the second time, there the third time, then what you're going to end up with is a random error. Systematic errors, however, are nice because they're always the same amount. All right, so you're going to get the wrong answer, but you're always going to get the wrong answer by the same amount. So that would be more indicative of this kind of situation, right? Where your errors are close to each other, but you're just not accurate and always by the same amount. Can you think of any situation that might give you a systematic error? Stop the video and have a think, maybe. One of the most common systematic errors are called zero offset errors. That basically means that you are using an instrument that was not put on zero in the first place. So when you started measuring, it already had a 1 on it. That means that all your readings are going to be +1. As you can see here, this voltmeter has an offset error of about 0.3 volts. So all of your results will look off by that amount. Now, what are we aiming for? We're aiming for experiments and investigations that are precise and accurate. Now, if you have precise and accurate results, that means you've got no systematic errors, no random errors. But each of these are associated with a different kind of error. Test yourself now to see if you can figure out which one of these situations, or each of these 3 situations, are affected by which kind of error. Stop the video and have a go. Well, this first situation is guilty of having a systematic error because all of the results are off by the same amount, but there's also a lot of random errors. And random errors are there because of a poor instrument or just a poor method. Precise and not accurate. All you've got here is a very clear indication of a systematic error. This one here is accurate, but you obviously got random error situation going on here. Now, we will go over this as we do experiments, but there are things that you can do to try and improve the results that you have. Precision can be improved by repeating measurements. As you take repeat measurements, it's important to be awake and conscious as you're writing your measurements down. And if there are any random measurements, just, be cautious to them and perhaps just repeat it so you don't write down any measurements that really stand out. Try it again. If you're getting a lot of random measurements, it could be your technique or your methodology. Accuracy is to do with your instruments usually, so check that you've got starting from a 0. Check by using a different method. So if you really want to, what you can do is actually look at your experimental setup and start again. But I tell you what, we'll come back to these as we start doing experiments.